So all right, please like and subscribe. All right, measurement of concentration is what we're looking at. And we're looking at the word solution and ions, and it's important that you get these words right. I'm going to introduce you to some new jargon that you need to become familiar with. Okay, so we're looking at calculations involving mass and concentration and volume. So those things together will require you to then convert things to moles, okay? And by extension, we're going to learn how to calculate pH as well. Titrations are important because that's the new practical that you'll be potentially assessed on, because we've taken away the lead iodide growing new organs experiment. Okay? The word, the molarity is the word we use to describe concentration in moles. Okay? So that word there, calculate molarity, if you like, calculate the what? That means concentration in moles. In other words, it's talking about moles per liter. Okay? Let's see if I can write. Yeah, moles per liter. Excellent. Let's keep moving. In terms of language, oh, I can't go back. That's cool. Oh no. Why can't I go back? That's actually annoying. That's okay. I'll just write it on this new slide. The words are solvent, solute, and solution. They are all referring to different things while simultaneously relating to the same thing. So the solution is the whole thing. It's the liquid and the thing dissolved in the liquid. Okay? So in other words, salty water. Salty water, where you've put salt into the water, the whole thing would be described as a solution. Then the other two words are referring to the dissolved substance, which is the word solute. Okay, solute is the dissolved substance. That is dissolved. So in this case, in my scenario of salty water, that would be the salt. Yeah, the salt. It'd be the salt. And the solvent would be, in this case, the water. The way that I remembered it when I learnt this was I was like, oh, look, there's a V in the word solvent. That means volume. Volume. So the word solvent has a V in it, and my brain just goes, oh, V for volume? That is referring to the liquid. That's really dumb, but it worked for me because they're all S words and they all mean three different things. So it's important that you figure out what the different things are. So if you were to draw a diagram, you're like, ooh, this is my beaker, and here's my water. And then you go, ooh, there's water in there? Is that blue? I'm colorblind, I don't know. Let's say that is blue. Cool. So we have H2O, that's the solvent, V for volume. And then we have the itty bits of sodium and chloride ions. The NaCl, that's the solute. And then the whole thing is the solution. Is that cool? Everyone happy? All right, let's move on. So, there are, fortunately for all of us, 4 different ways to measure concentration. However, the one that we use the most is molarity, which is concentration is equal to the moles divided by the volume. That is the most useful one for chemists. Okay? So, there are 3 other ways to calculate concentration. We can do it by grams of stuff. That's concentration in whoever's abbreviation that was. Parts per million is milligrams per kilogram. So that's often used in environmental science where they say things like, oh, that's 5 ppm. That just means 5 parts per million, which means literally 5 milligrams per kilogram. Okay?
So million milligrams in a kilo.
Yes, sir. Hence, literally part per million. George just big brained it. And then grams per liter is literally grams per liter. All right. We are focusing on the last one. Let's go. Okay. In terms of all of the ways that you can look at concentration, we look at the solute first, and then we look at the volume or how much solution there is. And we've already been through this, but there it is. Concentration is equal to moles per liter, or molar concentration as it's known, or molarity, which confusingly is given the symbol capital M. So you might see I've got 1.0 capital M HCl. In that context, it does not mean molar mass, it means molarity. So if you see that, don't be alarmed, and you feel like, but why science? Why the same letter but 17 different meanings? And the reason for that is because we only have 26 letters. Okay. I'm hoping that this slide makes sense. Slide number 8. If you've got a concentration of 0.5 moles per liter, that means that you have 0.5 moles in a liter. Okay? Yep. He does. And that's how you calculate it. Let's move on. Yep. So again, again, we want to. Again, the way to calculate this also requires for you to change the formula. Okay. Calculate the number of moles of sodium chloride needed to prepare a 500 ml of 0.08 moles per liter of salt solution. Here's one way to think about how to solve this type of problem. And you can start by doing listing the information from the question and then writing down the correct letter associated with that unit or measurement or whatever it is, quantity. and then using that information to figure out the formula. So what I mean by that is I go, in my question, I want 500 mils, so that's a volume. So you'd go, well, V equals 500 mil, and then you might want to then convert that. And then you go, well, this number here is a concentration. How do I know? How do I know that this is a concentration? Moles per liter, and then you go C equals to 0.0800. And then the question says, tell me the mass. Okay, so we're looking for mass, and all we have is concentration and volume. So then you go, okay, I know that these two things, volume and concentration, are connected together in the formula C equals N over V. And then you go, well, that means I can use this formula to determine number of moles if I rearrange the formula to do this. Okay? And then I see, oh, now that I know moles and I know mass, so I'm trying to figure out mass, I know that this formula, N equals small m over big M, connects those two things together. And then I know that I can figure out the molar mass of salt. And then I can use that information to then calculate the mass. Does it make sense? So if you read a question and you write down what those things are with the letter that they represent, that can help you figure out what formula I need to use to then do some calculations. Okay? Okay.
Whoa, Fred. Fred Ollie. Oh, it's 0. I was wondering why I did that wrong. No, Ollie, bring it back again. That's what I did.
Water, but side note, not side note, this note, main note, the density of water is pretty much 1 gram per mil. So if you had 200 mils of water, it should weigh 200 grams. Because each mil is a gram, or a gram of water is a mil. Now that's slightly incorrect. It's slightly incorrect because pressure and temperature will change the volume that water will take up. But for all argument's sake, for every calculation you ever need to do with water, that is the assumed density of water. In fact, no, 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 not in here. No, it is assumed knowledge. All right. It's not in the information sheet, which means you need to know it. But I think that's pretty straightforward. A gram of water takes up a mil, and a mil of water is a gram. Same number.
Oh my god, I think I got it right.
Okay. Thanks. Okay. Can we go to slide 16? Can you calculate all of that stuff? And don't look at slide 17, Gus. So, in your calculation, you would go, all right, I know mass, I know volume, and I want to know concentration. Concentration is C equals N over V, and I want to know this. I don't know that. I know this. Because I don't know number of moles, I need to use this. And then I know this from here. And then I can calculate this. And then that will give me number of moles, which I can use in the formula. And then I'll get my concentration. So we did the calculations. It's all there on the slides for you to follow. You should have ended up with 0.2 moles per liter. And then when looking at individual ions, you should have ended up with 0.4 for sodium and 0.2 for carbonate. And hopefully that makes sense. You might start noticing now that we have square brackets. The square brackets are used when talking about concentration. I hate you, Jack. All right, so we have another situation where we can do an example question. It says there that aluminium sulfate, Al2SO4 bracket 3. So sulfate is a type of polyatomic ion. It's a multiple atom ion. And on page 4, you will see sulfate listed there in the -2 column, Jack. So it's asking you, in a solution of aluminium sulfate, the concentration of sulfate is 0.05 moles per liter. What is the concentration of the solute? So it's important from this question that you understand the point of observation or what information you're looking from. Because we're looking from the sulfate, and we want to know the concentration of the aluminium sulfate, it's telling us the concentration of sulfate. Therefore, we are dividing by 3 to find out the concentration of the sulfate, aluminium sulfate. Does that make sense? Because it's telling us the concentration of sulfate, and we know for every aluminium sulfate, there are 3 sulfates per aluminium sulfate. So if I have a concentration of 0.05 moles per liter of sulfate, I would divide that number by 3 to find out the concentration of aluminium sulfate. It's the reverse of what we've done in the previous question. Yeah?
Why would you lie about this?
We're dividing by 3 because it's telling you the concentration of sulfate, not aluminium sulfate. Why 3? Because for every aluminium sulfate, we have 3 of them. See that 3 there? So it says the concentration of sulfate is 0.05, and then it says find the concentration of the solute, which is the whole thing. So because for every aluminium sulfate, there's 3 sulfates, and we know the concentration of sulfate, we divide by 3 to reverse that. Because if it said the concentration of aluminium sulfate is 0.05, tell me how many sulfates there are, you would multiply by 3. But this is telling you the information the other way around. Yeah, but it's not asking you about that, and it's not giving you information about aluminium. It's only giving you information about the sulfate. What? Okay. All right, it's like this, right? Let me simplify it for you. If we've counted 40 wheels on cars, how many cars do we have?
That's pretty high.
We're not going to count the spare wheel tire. Let's assume all cars have 4 wheels. 10 cars, right? Does that make sense? If we have 40 wheels and each car has 4 wheels, how many cars do we have? 10. Why do we know that we have 10? So you divide it by 4, yeah? That's the same math.
I just don't understand. 3. Surely.
Um,
You took 8 screenshots.
did I? I'm sorry. All right, last slide with soul dilution. You're lost? Okay. Uh, so now what we're seeing is subscript for moles. We've got N1 and now N2. The reason for that is because maybe in a question you might be dealing with lots of calculations involving moles. And so therefore, it is important that you have a subscript to help you tell the difference between what you're looking at. So all this is saying is that if I add more water to a solution, then the number of moles is the same. Okay. So you're about to see a super formula, as in a formula equaling another formula. It is the same one, but I need to explain this to you so that you are comfortable using it, because if you don't understand this, you cannot do the second crack, as in you won't understand what we're doing. Okay? So, here we go. Can we all agree that concentration is equal to number of moles over volume? That's what the formula says. Yeah? That's what the formula says. Okay. If I rearrange the formula, I can rearrange it so that number of moles is the subject of the formula, where I get N equals C times V. Is that okay? All right. So, if we are doing a dilution and we want to know things like concentration and volume, we can make the assumption that if I make a dilution and concentration is changing, and I use this formula to calculate concentration, then on the assumption that the number of moles does not change, I can make these two formulas equal each other. In other words, I can do C1 V1 is equal to C2 V2. If number of moles remains unchanged when you add water to a solution, and how we calculate concentration has to do with number of moles and volume, you can make two formulas equal each other because they equal the same thing. So in the way that we use this is, if we add more water, then the change should be in proportion to your initial solution. So what we are now working with is two formulas equaling each other, and I want to run through how we do this calculation here. So on the assumption that number of moles remains unchanged in a dilution, you can do calculations to help you figure out volume or concentration when doing a dilution. So this question reads, what volume of a 10 mole per liter stock hydrochloric acid is needed to prepare 250 mils of a 2.0 mole per liter hydrochloric acid solution? So, ignoring all of the things that are there, you go, all right, C1 and V1 and C2 and V2, the way that you set up the formula to then do the calculation is by remembering that the 1 is used for initial and the 2 is used for final. In the initial situation, the thing that we're starting off with, we've got a concentration of 10. And then in the final, we want 250 ml of a 2 mole per liter concentration. So we would put the 250 here, and then we would put the 2 there. And then the question says, what is the volume that I need? So this is what I'm trying to figure out. So with this super formula, where there's 4 things I need, 4 things there involved, I know 3 of them. You just need to put them into the formula, and then it'll tell you exactly how much volume of the acid you need to make the acid that it's telling you to. Okay? So when you rearrange this formula and the thing you want to figure out is V1, can you see that V1 is multiplying C1? So if you want V1 to be by itself, you need to divide both sides by C1 to get C2 times V2 divided by C1. And then you just put all the values in, remembering to change this into liters. And then you can figure out the volume that you need. Yep.